presentation will explain what a carburetor is, how it works, and demonstrate the principles using fluent modeling software. What is a carburetor? A carburetor is a device that relies on the principles of fluid mechanics to create the proper mixture of fuel and air before that mixture enters an internal combustion engine. Carburation is how many older automobiles deliver the mixture to the engine. For the most part, carburetor use in cars has disappeared and been replaced by fuel injection. Fuel injection utilizes a fuel pump, multiple sensors, and a computer system to create the proper mixture for combustion. Fuel injection is more complicated and expensive, but is more reliable and allows for much finer tuning of each engine. Carburetors are still used on many motorcycles, ATVs, lawnmowers, and other small engines today. How a carburetor works. The design of a carburetor is based off of Bernoulli's principle. As area is decreased for a fluid flowing through a pipe, the fluid's velocity will increase, causing the static pressure of the fluid to decrease. The venturi tube shown displays the principles in action. At the smallest area of the tube, the area of the lowest pressure of the flow, a fuel inlet is placed that makes fuel available. Note there is no need for a fuel pump, however some engines use an electric pump to feed the carburetor. Some sort of regulating device such as a diaphragm or float is used to keep the amount of fuel available at any given time constant. Parts of a carburetor. The image on the left shows what a motorcycle carburetor would look like if you were to remove it. The image to the right shows a very simplified sectional cut of the carburetor. Once the engine is running, it will draw as much air as it is allowed. The engine draws air through the air filter and into the upper part of the venturi tube. The air continues through the throat of the tube, where its pressure is decreased greatly. The decreased pressure draws fuel from the float tank, creating a mixture of fuel and air. Note a ratio of about 15:1 is desired. The mixture then continues to the lower part of the venturi tube where it enters the engine. The throttle valve, shown here, is used to regulate the amount of air allowed into the engine. The position shown indicates full throttle. The choke valve, shown here, can be turned to limit the amount of air allowed in without limiting the amount of fuel. The choke is used for cold starts as a higher fuel to air ratio is desired. Physical model. For simulation, the carburetor is treated as a simple venturi tube with a single fuel inlet, shown here, placed at the throat of the venturi tube. The air will enter in through here and exit out the bottom. The image to the right shows a mesh of the model. Simulation setup. The simulation was set so that there were two inlets, one for air, one for fuel, and one outlet. Meshing was weighted towards all walls to improve turbulence modeling. Use of multiple species was enabled, with propane and air as the two selected species. The fuel was given no initial velocity, while the air inlet was given an initial velocity. The simulation was run multiple times with different initial air velocities. The realizable K-epsilon model is used as it works well with fully turbulent flow. A coupled pressure-based scheme is used for simulation. Results.
So now that the simulation has been completed, we're going to take a look at some of the results. If we turn on a pressure contour of the walls, you can see pressure is greatest as the air comes in initially. As the throat area decreases, velocity increases, which as expected, the pressure decreases, and then once it expands again, the pressure increases, not quite as high as it was initially. I'm going to turn on some particle tracks of particles traveling through the two inlets. So they are set to change color based on size as they travel through the system, with the fuel inlet being an inverse rainbow color scale. So if I turn off the air coming in, you can see that the fuel particles distribute themselves fairly evenly as is expected, and they are given no inlet velocity, but they are pulled in due to the lower pressure of the system. And then I'm going to turn on an ISO surface that displays anywhere in the system where particles traveling at 80 meters a second. This is done for comparison between three other simulations. This current simulation was run with the air inlet velocity of 20 meters a second. The faster model, which I'll show next, was set with the inlet velocity of 30 meters a second, and the last one was set with an inlet velocity of 2 meters a second. So now we're going to take a look at the faster model. So as you can see, if we turn on the particle tracks again, you get a fairly similar result. If you look at only the fuel, it spreads out, not quite as much because the air is traveling faster, so it'll take it a second to become more evenly dispersed. But again, pressure is lowest in the middle, fuel disperses as expected, which is the point of the carburetor. And then if we turn on the ISO surface where all particles traveling at 80 meters a second are shown, you can see there is less area where the particles are traveling 80 meters a second. This is because the input velocity is faster. Okay, so finally we'll take a look at the slowest model. And as you can see, if we turn on the particle tracker for the fuel, it spreads out as expected. Slightly more so than the last two because the inlet velocity of this one is only 2 meters a second, so it has more time to spread out. If we turn on the ISO surface, it will display any point in the flow where the particle is traveling 80 meters a second. There is no point in this one, which is kind of expected. With an inlet velocity of only 2 meters a second, you can't really expect the flow to accelerate that fast.
In conclusion, carburetors are simple devices designed to mix air and fuel appropriately before it enters an internal combustion engine. Carburetor design is based off of Bernoulli's principle. In reality, carburetor geometry is very important and is referred to as jetting. Slightly changing the way an engine is jetted will have a huge impact on how the motor runs. CFD can be used to model the jetting of a carburetor and produce the right size to optimize the efficiency of the motor.